Hello everyone. Today in this video we are going to show another exciting new feature and new sub-software or subsystem of our software Vidyutik Urja Prabaha PravahaSim. For that we came to our app. Now we need one power system transmission network. We already have a demo 9-bus system and we are going to fetch that from our computer. Here I am going to fetch the 9-bus system from my computer storage. Here is the 9-bus system. You can observe a change in the component from our previous video that instead of wind turbine, a wind farm component is connected with bus number 3. Now the sub-software which we are going to introduce and demonstrate is Wake Effect Integrated Wind Farm Designer, and the effect on Wake calculated wind farms connected to grids for fault-induced frequency stability or voltage dip-induced frequency stability analysis. As in modern power sector, non-conventional or renewable energy sources, integration is increasing day by day to reduce the environmental pollution and others. So there is a problem with those renewable energy sources that they don't have their own natural inertial response, but conventional synchronous generators have them. So as the renewable penetration increases in power grids, the system inertia gets reduced, which affects severely during any fault or contingency. During any fault event in high wind penetrated systems, such as near about 50% wind penetration, as the wind generators are not directly coupled with the grids, if connected to the grid using power electronic converters, so they are decoupled from the grid and not able to sense the change in the grid and also not able to recover automatically. Wind generators need some manual or predefined control strategies to recover from the fault. During this manual control strategy activation, it takes some time, during which the system frequency dips very much higher than the conventional synchronous generator connected systems. So these phenomena can be simulated using the future fault-induced frequency stability analysis in our software. Now, wake effect calculation is also a very major concern for wind farm connected grids, as wake effect calculation is a crucial part of the total analysis. The wake effect in wind turbine is a reduction in wind speed and increased turbulence that occurs downstream of an operating wind turbine, which causes power reduction from wind farm and causes more frequency instability during any contingency. Now I am going to show you the effect and the importance of wave effect calculation and how to do that using our software PravahaSim. So now first I am taking the 9-bus system, and now I am designing the wind farm using the sub-software. Here you can see the wind farm is connected to the bus bar 3. Now if I click on the wind farm co-app, this button, then it will ask for which wind I am going to design the wind farm. So now only one wind farm is connected to in this total 9-bus system, so only one option is there, wind farm 1. Now I am going to click on OK. After that, this subsystem or sub-software is opened. It is a wind farm designer sub-software with wake effect integration. Now I am going to insert 4 wind turbines and going to place that turbines accordingly. Here you can see 2 turbines per series, and like that in a parallel combination 2 series combinations are there. Now I am going to select the wind turbine model. I am selecting the Vestas V90 3 megawatt wind turbine. This model is common for all 4 wind turbines. Now I am going to changing the wind speed. Suppose I am giving 13.5. You can give anything. Now after that, if I click on the synthesize button, then you will get a result like total wind power is 8.52 megawatt. Now for east wind direction, you can see the this wind turbine 1 and 3 get the full wind speed so higher than the wind turbine 4 and 2, which is downstream wind turbines. So they get less wind compared to 1 and 3. So with 1 and 3 wind turbines power it is 2.91 megawatt, and for wind turbine 2 and 4 it's 1.35. If I change the wind direction, suppose I am giving the southwest direction, so wind turbine 1, 2 and 4 will get the full wind speed, but wind turbine 3 will get the less wind speed. Now if I click on the synthesis button again, then we get the total wind farm power like 10.4541 megawatt, and yes, you get 2.91 for both of 3 wind turbine 1, 2 and 4, but for wind turbine 3 we get the less power like 1.68 megawatt. Now after that, when you satisfied with the wind farm modeling, and get the required power. Then if you click on the transfer button, then you can see the total power transferred to this wind farm block. You can see that active power is 1. There the active power is showing in megawatt, but for our load flow and fault analysis purpose, we converted this to per unit value with base power as 10 megawatt. So from 10.41 megawatt to 1.041 per unit value. But with this, we have to give some additional inputs, like reactive power is showing 0.0, which we have to change. So I'm changing that. If I click on the set other wind farm parameters, then this pop-up will open. Here the state is showing that this switch is off and mode is PV. If we want to change from PV to PQ, then we have to on the switch. I will click on the switch. The switch is on, and here it is also shown switch is on and mode is P2. Now we have to keep the value for reactive power. So we are suppose we keep the 0.04 per unit reactive power. After clicking, you get the entry is PQ mode and reactive power is 0.0. After that, you can check in the bus details that power is changed, that active power is that much, reactive power is 0.04 and mode is PQ. PQ bus for wind comparated bus, that is bus number 3. So now after that we can do any kind of Y bus calculation or neutral action calculation, or directly we can go to the fault analysis. First we so using LG fault analysis, after clicking on run, you get the for analysis for LG fault. After that, if we do the fault induced frequency stability analysis, for that we click on the code editor button. That is our inbuilt code editor. Here you can see that in our code editor you can get a demo code. You can change any component value, but we are not changing anything now. All things are set, so I am clicking on execute turbo. After clicking, you get a frequency curve which is showing after initial spike. You can see dips very much higher than the conventional generator connected systems, as wind penetration is near about 50%. And after that, late recovery is there. After recovery, it settled to some point below the near about the initial point. So here you can see that what is the frequency value. You can see that optimal frequency is 49.47 Hz, but after the fall, the frequency dip is 46.23 Hz, and recovery is 48.45 Hz. So like that, you can check for double LG fault also. You can check same thing. You can click on execute. You get the frequency dip, and here for a double LG fault, for the all other conditions same. The frequency dip is 45.52 Hz. And for triple LG, it is 45.20 Hz. So as we see that after effect calculation, the power is 10.41 megawatt. But if we don't calculate the wake effect, then we have to assume that all wind turbines get the same wind speed. So they will produce same power. So instead of in this wind turbine 3, instead of 1.68 megawatt, we have to assume that we will get 2.91 for all the wind farms. So if we assume so the total power will be 2.91 into 4, it's 11.64. And after dividing it using base power, that is 10 megawatt, we will get 1.164 per unit active power. So if we cut this and manually input this value, that is our 11.64 by 10, it's 1.164. Then I'm selecting PQ mode, 1.164, and reactive power we are put it remains same, like 0.04. If we take the bus details now, it is 1.164 and 0.04 PQ bus wind farm. So now in this scenario, if we check the LG fault analysis, then we will get slightly lesser frequency drop. Means what we get after wake effect calculation, we will get less frequency drop during without wake effect calculation. So for LG we get 46.77 Hz. For double LG we get this value near about 46. It's 45.99 Hz. And for triple LG fault we get the frequency value as near about 45.65 Hz. So if we compare all those values with the wake effect calculated and wake effect not calculated frequency dips, then we get these results. So first for these fault types, I'm calculating the wake effect. So these values are without wake effect frequency dip, and these values are with wake effect frequency dip. So the differences what we get that without 46.77 Hz and with wake effect 46.23 Hz, and the differences is 0.54 Hz. And similar for double LG fault from 45.99 to 45.52, difference is 0.47 Hz. And also for triple LG fault 45.65 to 45.20, difference is 0.45 Hz. And these all are the differences. These all are the differences. You can see near about 0.5 Hz difference is there on an average, which is a significant frequency difference, and it is very important to calculate this frequency difference, which can impact the kit severely. So after that, we want to say that wake effect takes a very crucial role in this fault analysis portion. And so at last I want to say that I think this new software, this system is also a very crucial analysis feature for modern renewable grids in our main software PravahaSim. We hope this feature will help the user in their different analysis. We firmly believe that our suggested software will be a competitive alternative to the commercially available foreign software packages. It will help engineers, industry and academia immensely. For more details and download, visit our website www.pravahasim.co.in. Thank you.